Hello. In this video we are going to compare the general linear model that uses least squares, analysis of variance with repeated measures. We're going to compare that to the proc mixed model of repeated measures that uses maximum likelihood as a way of calculating the F ratios and the other things. The general linear model, the least squares method, uses a formula and takes the data to directly compute the parameters. The least likelihood method uses an iterative process to find the best parameters that reproduce the data. Now in this case, in the case of our example here, there is no missing data and the n's are equal, so the results should be the same. Now let's see if that's what happens. So first we're going to look at the general linear model's repeated measures. And this is the Chow data, and to remind you, it is actually, in order to use the repeated measures in general linear model, it has to be in a horizontal orientation. So we come over here and we're going to look at the change in axial length over years. So we have axial length 0 at baseline, 1 year, 2 years, 3 years, 4 years, 5 years. But notice it's horizontal in its orientation. And then we have lens type over here. Now, I, of course, is not an eyes are not independent, so our left and right, we have subject 1 here, and we have subject 1 up here, and that's at least within subjects. So the observations are not independent, and we cannot use the general linear model for doing this. So we have to actually split our file by eye to preserve the independence, because eye is in a vertical format, and it just doesn't work. All right, so we go to Analyze, General Linear Model, Repeated Measures, and then we have a factor, and we're going to call it year. And there are 6 levels, 0 through 5. And so that's our repeated measure, year. So each person is measured each year for 6 times. And then we have to fill in those repeated measures there with variables. So we come down and we highlight 0 through 5, and it fills that in. Now, our other factor is between subjects. That's going to be lens type, and that's going to go there. We're going to look at the means, and we have lens type, year, and lens type by year. Now here we're not doing an analysis of covariance where we look at baseline, control for baseline, and look at the rest, where this is a one-way starting at year 0. So we have lens type, year, lens type by year. So we have 2 fixed factors, lens type and year. And let's see what that gives us. So we have 94 subjects in the left eye, 83 in the right eye for each of the 2 groups. This is our multivariate tests. This is a formula that if you were thinking y equals a plus bx, it's y0 to y5, y1, y2, y3, y4, y5, al 0 through 5. And equals a plus bx, whereas x is lens type, either a 0 or a 1. And so it's multivariate, multiple variables on the y and over on the x. This does not have any, like we have the assumptions of the sphericity. There's no sphericity assumptions required in this. It's like a t-test with multiple dependent variables measured all at once. We do have a significant effect. The error covariance is not equal across all places. And so we get a number of adjusted degrees of freedom. Notice our F statistic is the same all across the board. It is just the degrees of freedom that change based on adjusting for either Greenhouse Geyser or Hunt-Felt by this sphericity coefficient, this epsilon. These are the within subjects effects of, and we have for left eye and right eye, year, and year by lens type. So those are measures within, and we have the right eye. We have our contrasts, so linear and quadratic. We looked at this in a previous video. And then we have between subjects. Now the between subjects main effect is significant, but since the interaction is significant too, year by lens type, we care more about that in looking at those things. Now when we just go straight out, we can't do the, we can get the interaction term, we don't get the paired comparisons. So we could plot these and see what happens. In fact, let's copy this into a spreadsheet. And let's do a graph. Now notice that it gives us it takes this as numbers 1 through 6, and the problem is it's doing them as numbers as well. We don't want that. We're going to get rid of it. We're going to go in and we're going to select our data. We're going to edit our chart. Now we're not going to be able to edit that now. But instead of 0, it starts at 1 and it goes up to 6. So you might have to change that at some point. It does have spherical lens in there. Let's add another one. Let's call this aspherical. And we can see what happened there. Oh. Let's move that over to there. I'm not quite sure what happened there. Well, we're going to let this go for the moment. It somehow replaced that mean with the word spherical. I must have pushed a button along the way someplace. Let's go to our output. Let's just try it again. Copy, paste, and then there we go. We can also make the years go 0, 1, 2, 3, 4, 5, which matches our AL0 and so forth. And we can come down here and select data again, go to edit, copy this. You could also make it AL0, AL1, highlight these two, and we get our variable names down there. Alright, so let's just come over here. Let's copy our within subjects effects so we can compare them. All right, now let's look at this. Let's do a proc mixed. And so what we're going to do is we're going to call up a different data file. Still looks pretty much the same as the other one, except that now we have axial length and we have a variable called year. So let's do a data sort ID and year. And then we seem to have a lot of junk stuff here. Let's get rid of some extra unwanted variables. Goodness gracious. Here we go. 700. And we also have a bunch of columns that we don't need anymore. Clear. But the point is that we now have left and right eye. We could add this into it, but just so we can compare directly, we're going to split by eye in this file as well. And then notice that this is subject 1, 1, 1, 1, 1, 1, 2, 2, 2. This is a vertical format where we have the data laid out vertically under axial length, year 0 through 5, 0 through 5, as opposed to horizontally. This is the format required by proc mixed. So analyze mixed model, linear. Now it asks, what is your subject variable? It's ID. What is your repeated variable? And again, it's year. And then this has this other aspect to it. It's asking, what is your repeated covariance type? It starts with diagonal, which means that there's no correlation. It's completely independent. Ones are in the diagonal of the covariance matrix. So think of a correlation matrix of year 0 through 5 by 0 through 5. And the diagonals of that would be AL0 to AL0, AL1 to AL1, AL2 to AL2. Those, they're perfectly correlated because they're the same thing. Whereas all the off diagonals, say AL0 to AL1, is a correlation. And that in this diagonal, that correlation is assumed to be 0. We can with great confidence say that the correlation of person's year the previous year is pretty similar. So those correlations aren't 0. We're going to, at least at this point, use compound symmetry, which is one that we use most of the time. Now, I will say in this case, that's probably not the best choice, because the idea is that the correlation between axial length at baseline in 1 year is the same as the correlation. First of all, the correlation is greater than 0, and the correlation is the same between baseline in year 1 and baseline in year 5. That's probably not true. The correlation probably decreases over time. But our goal here is to compare this with the GLM model, and GLM does not have the concept of being able to vary things over years, whereas this one we could use this AR1, which is autoregressive, and that is that very thing. It says that years that are closer together are more correlated than years far apart. All right, then we continue. We have our dependent measure. There's only one in this case. We don't have all 6 measures to go. Just have axial length. We have year as a factor. We have lens type as a factor. And I put them in this order because I want year to be listed out for each lens type, as opposed to year baseline comparing the two directly for graphical purposes. One of the things unlike in GLM, we have to specify the model. And we want lens type and year, and there's a factorial button, which could also be main effects or interaction, and so forth. If we were doing analysis of covariance, and we assumed parallel lines, we would do the main effects. In fact, let's see what that would do. Main effects would just bring over lens type and year. But we're doing a full factorial analysis, so we do that. Highlight these two and it adds the interaction term. We want our means. Each of these. Again, it doesn't do, even though we say compare main effects, and it's not going to do the interaction term either. So we have to kind of hack it and put in the contrast specifically in the syntax, but we're not going to do that right now. And then we can also do statistics, which probably should have done before, but we'll look at our parameter estimates. We can test the covariance parameters, which tells us if our variability is greater than 0 within subjects. This is kind of testing to see that that there is within subjects variance that we have to worry about, and we hit continue. Really, that's not one that you normally have to worry about. All right, so what do we get? We have the model dimension. It says there are 6 years, there are 2 lens types, there's 12 combinations of lens type and year for both the left and right eye. We have this thing called an information criteria. We didn't get that in the GLM model. This is basically a guide to helping us know which model fits. We had, when we defined our compound symmetry and we said the autoregressive would probably be better, we would be able to determine that by looking at these numbers. And smaller number, more towards negative infinity, because sometimes these are minus, is better. So a smaller number here is better in terms of fit. When you just run one model like this, you just get one number that has been calculated in a number of different ways. And this is a kind of a goodness of fit criteria. So here are fixed effects. Now notice in the GLM we had a within subjects and a between subjects and separate. Here they all come at the same place. But notice there is no error term given here. So I kind of, let's see, let's put that over here. So we don't have all the sums of squares and mean squares. There are no sums of squares and mean squares. Those come from specific formulas doing it with the least square method. You don't really see the direct effects. I suppose you can choose an option that lets you in on that, but the normal output doesn't just automatically give that. These are the estimates of the fixed effects. Now, if you look at this, there's a term called intercept, and there's a lens type, and this is 0. If the lens type was spherical, 0, you would add 0.64 to the axial length. If it was year 0, you would subtract 42 millimeters. If it was year 1, you would subtract a little bit less, a little bit less, a little bit less. So what this is doing, this coefficient right here is saying at year 5, spherical lenses are 0.64 millimeters greater than aspheric. And so they're shorter, and then that shorter is a little bit less and less and less. For at baseline, they're closer, just 40, but they're still 42 points apart, which is pretty far. So that's how that works. But this is exactly a regression equation. It's y equals a, axial length equals a, intercept 24.9, plus, if lens type is 0, 0.642. If lens type is 1, then nothing. X is 0. Even though the labels are, this is our value from our data at 0 and 1, the computer is actually making lens type 1 0 and spherical 1. It's a little confusing. I think it might give you a little note up here. No, it didn't. That's nice. Anyway, it does here, and it tells you which one is indicated. These are indicated variables, and so they create dummy variables. So rather than just having year and making it a linear thing, it's fixed, and you can see that it's a good thing it's fixed, because wherever you are on this, it's a little bit different. Which it actually looks pretty linear, but we saw from before in the GLM one that quadratic is important too. So this is 12 points apart, this is 3, this is a little bit more, this is less, and so it kind of bounces around a little. Anyway, so this tests each one of them. So it's y equals a plus bx, or yeah, bx plus b1 year 0 plus b2 year 1 plus b2, and so forth. So it's a regression equation. It's exactly what you would get if you did a regression analysis. Well, sort of exactly. This takes into account within subjects, which normal regression wouldn't. Now then, we have, instead of mean square error terms, we have this estimate of covariance parameters. We're going to copy this and we're going to put it down in here. Now, if you recall, this mean square error here, so this is the mean square error column, and it has it in these different formats. So to get the pooled standard deviation, we take the square root of that value, and we get that if we assume sphericity. But we saw we rejected that, so let's see what we have. So here you have 4 different estimates of what the standard deviation is. This is for the left eye. Now down here we have a left eye, and in the mixed model you don't get a bunch of different ones. You just get one. You get one for each of the covariance models you try for, but in this case it's the estimate of what is the CS diagonal offset. And so if we come up here and let's put it over here, equals the square root. Again, just like in mean square error here, this covariance estimate is the square root of that. So you can see it's pretty close there. What if we go down here? Whoops. Go down here. We can see it's assuming it doesn't take into account the sphericity. It is as though sphericity was 0. And so we might be, in a way, inflating our F statistic in terms of that. But this is what fits the model in terms of this covariance. And actually, this covariance is going to go smaller the better we fit. So you get, in a way, you get a similar answer. In another way, you get a pretty different answer. So our F statistic for lens type, which is, I didn't get that. So we'll just do year. The F statistic is 10. The F statistic for sphericity for year is 130 right here, 0.941, and over here it's exactly the same thing. And for the interaction term, it is 31 and 31. You can see those are the same. Now, I don't know if we will be able to see. Okay, why isn't it like that? It's just 0. We copied it over and we got just 0. Okay, so what's going to change is the degrees of freedom. This one has 5 versus 1.69, 0.71, and 1. So we're getting a little bit different. Well, actually, 5 degrees of freedom. Yeah, it's the top one. So, so we can see from our proc mixed and our GLM, we get the same F ratios, and the p-value is going to be the same as if we ignored sphericity assumptions and sphericity corrections over here.